Hello, this is a quick introduction to the concept of random variable and probability distributions. This will be a lecture of 15 minutes duration, and there are some references given. You may look at it, for example, analysis of third edition by Royden, but I don't think you need this if you follow this presentation carefully. So far we have introduced the concept of a probability space. To recap quickly, I have a non-empty set S which represents the outcomes of some random experiment, and I have a collection F of subsets of S which we call a sigma field, and this is closed under a union, a complement, and the whole set S is there, and probability is a function defined on this collection. So together this triplet is called a probability space, and we have investigated the properties of the probability function in detail. For instance, the Borel-Cantor lemma and the continuity theorem are two important properties that we have studied in their statement proofs and application of Borel-Cantor lemma in up to the last lecture. Now today I introduce one more concept. So given a probability space, I can define a function x. I am denoting the function by capital X or Y. So this is slightly different notation from analysis, because in analysis we denote functions by little small f, g, etc., h, etc. But here it is a matter of convention that we denote the functions by capital Roman X, Y, Z, etc. Of course, A, B, C, D are not used for function. Generally X, Y, Z, these are the standard notations for functions. So here I am defining a function on S. So this is a function with domain S, and for every w in S, xw is a real number. So it is a real valued function on S. And so x is a mapping from S to R. This is called a random variable if it satisfies certain condition that for every real number y, if you look at the pre-image of this open interval y to infinity, then that must be in F. So what is meant by the pre-image of the open interval y to infinity? So we are looking at those points in the domain for which xw exceeds y. This condition is exactly same as the condition in the definition of a measurable function on a measure space. So we can think of this as a measure space, because I had mentioned in the beginning that probability is a measure. Axiom 1 and axiom 3, these are the two conditions that are the properties of a measure. Here of course you have got an extra property, probability of S is 1, but nevertheless OPP is a measure. So on a measure space you can define the concept of a real valued measurable function. That is a starting point in measure theory. So you can look at real analysis third edition by Royden. The concept, this is one and the same. So basically a random variable is a measurable function on a probability space. Now simple random variable, now the concepts are analogous. So now you have heard a simple function, right? So similarly we have a simple random variable. So this is a random variable where the range is finite with probability 1. That means it is taking only finitely many values. Suppose xw is either 0 or 1. So then that will be a simple random variable. So you can collect all those points in the domain for which xw is 0, and you can collect all the points in the domain which xw is 1. These two will be disjoint sets, and together they will be a partition of S. So this is the idea. So whenever I have got a simple, so examples of simple function, that I toss a coin, so count the number of heads. So now a 1 in a single toss, it will be either 0 or 1, because you can have at most one head. Similarly, if I toss a coin 10 times, then ask you to compute the number of heads, it could be 0, 1, 2 up to a 10. So here it takes 10 many values. So whenever we talk about a simple random variable, we refer to a measurable function in a probability space where the range is finite. And since the range is finite, so you can split the sample space or the domain depending upon the different values of the random variable. So if the random variable is taking values a1, a2, ak, you can split the sample space. So let me write here a bit. So if x is a mapping from S to X to the set A1, AK, if S is a mapping from A1 to AK, then we call it a simple random variable. And in that case, if you define, in that case, oh, by the way, I leave it as an exercise to check that whenever you have a mapping like this, that is the range of X is finite, this condition of measurability will be automatically be satisfied. Okay, so then you don't have to bother about this condition, it is already set in that case. So if I define a set AK equal to AK, okay, I have written, let me make it M, then it will make sense. So then K equal to 1 to up to M forms a partition of S. So I leave it as an exercise for you to verify. Okay, you will do that. So you have to very convince that AI intersection AJ is phi and the union of is whole of S, and that's not difficult because for every W in S, XW by the definition of mapping could be any one of these numbers, right? One at a time. So you collect all those points which are in A1, then you collect points which are in A2, then you collect all points which are in AM. Obviously no point in S is left out, right? And there cannot be no point W can be simultaneously mapped onto A1 and A2, right? That would violate the definition of function itself. So it's not a surprising thing. So whenever you have a simple function like this, you actually have a canonical representation. So we could write that XW is equal to summation of AI into indicator of the set I, indicator of this set. So if you want to know what I am talking, you can just look at Royden at the characteristic, that canonical representation of simple functions. So next, discrete random variable. Now discrete random variable is an extension of this idea. So here the range is finite. Instead of finite, if it is a countable set, so then it will be called a discrete random variable. So this is to a set. So here, let's say it is mapped onto this an, where n is a natural number, natural number, NUMBER. So this is then a discrete random variable. So then you can then you will get a countable partition. Okay, with why we say with probability 1, it's a practice, right? That means if there are some points which are mapped to something else other than these numbers, then they will have probability 0. That is what it means with probability 1. So I am saying this with probability 1. Meaning what? Means that if for some element in S, XW is not equal to any one of these numbers, collect the such elements will constitute an event or a subset of S that has a 0 probability. So you can say that it is like the concept of almost surely in measure theory, which basically means almost like pointwise. So collect for every W, XW will be one of these numbers with probability 1. So that's it. So now there are some examples of discrete random variable. So simple random variable, we have two examples, 1 and 2. Here there X is taking finitely many value, and here I am having a point of, so now the discrete random variables obviously will occur when the sample space is infinite and countable. So you cannot have a finite sample space and a random variable that takes infinitely many values. That cannot happen. So when we are talking about uncountable, so that when we are talking about a random variable that is taking infinitely many values, obviously the underlying random experiment has infinitely many possible outcomes. So therefore, suppose one such example is that a coin is tossed until the first head occurs. So x is the number of tails preceding the first head. So then you can easily see this is a familiar example to us. We have seen this example in the context of a random experiment having countably many outcomes. So the xh will be 0 because there are no tails, xth will be 1, xtth would be 2 in this way. When you have tth, that will be n is the number of tails preceding the first head. So in this way, so this is the idea. The random variables are real valued measurable map. Simple random variables are real valued random variable where the range is finite with probability 1, and countable random variable or discrete random variable where the range is a countable set with probability 1. Now what do we mean by probability distribution of a random variable? So now we have 4 things. One is the sample space, the collection of subset P. So we have a probability space and we have a concept of a random variable on this. So now we can ask questions like what is probability x equal to y, or what is the probability that the value of x is between a and b, and in general we can ask, since x is a real valued function, so we can ask what is the probability that x is taking value in some Borel set. So these probabilities will be referred to as the probability distribution of the random variable. So in particular, we define the probability distribution through a function called the distribution function, which is essentially the probability that if x less than equal to y. That means I have not written here explicitly, so that means this will be equal to so here this is the opposite of that. So probability of complement of this. So probability probability of the complement of this, that is x insert less than equal to y. So this is what it is. Remember, x is a mapping from S to R. So I am counting those points in the domain for which xw, which is a real number, does not exceed y. So that collection is an event. Well, why is it an event? Because x is by definition is measurable map. That means this is belonging to f. This now f is such a collection which is closed under complementation and union. So if you take complement of this set, it will be in this collection by definition. So therefore this probability that those points, this event that those points in the domain for which xw is less than equal to y is an event, so we can measure their probability. Remember, p is a function defined on this collection f, x is a function defined on s, but p is a function that is defined on the collection of events f. So therefore we can define this function. Now this will be called the distribution function. This gives me the probability that the value of the random variable does not exceed this number y. And now it is a matter of proof. So I am leaving this exercise for you, that prove that a probability x between a and b is f of b minus f of a. So now here you will have to use the finite additive property that you have proved. So I am leaving here up to now. So please try this exercise. Thank you.